Hello, class. Today we are going to be having a recitation on variational autoencoders. The first thing that we're going to do is give a brief overview of autoencoders, which Professor Biksha should have talked about a few weeks ago. And then we will go to the outline, and then we'll introduce some of the probability theory that's necessary for understanding autoencoders. Hopefully that isn't anything new, it's just a compilation of all of the probability theory that you'll need to know for variational autoencoders. And then we will give a basic overview of general models, which is the larger category that variational autoencoders exist within, like GANs, for example. And there's a few others that I can definitely name if I wanted to. Nevertheless, and then after the generative models overview, we will start discussing variational autoencoders in its entirety, including the a good dive into the probability theory involved with making them work. It's actually pretty interesting. So look forward to that. So I'm going to hand it over to Ewing now, who's going to start talking about autoencoders again. Have fun.
Okay, let's start the autoencoder recap part. If you remember, the autoencoders are an unsupervised learning technique in which we leverage neural networks for the task of representation learning. And the goal of autoencoder is to use the input to predict itself. Specifically, we will design a neural network architecture such that we impose a bottleneck in the network, which forces a compressed knowledge representation of the original input. As we can see in this picture, the autoencoder includes a encoder, which maps the input to a hidden representation, and also a bottleneck, which is a layer that contains the compressed representation of the input data. This should be the lowest possible dimensions of the input data. And also a decoder, which maps the hidden representation to the output. We can also call it reconstructed input. And of course, we will have a loss function, which also called reconstruction loss. This loss measures how well the decoder is performing and how close the output is to the original input. As we can see, the green box here of f function represents the encoder, and the orange box here of the g function represents the decoder, and the loss function is just minimize the difference between the original input and the output. We can apply autoencoder into many fields, such as data denoising, image imprinting, and information retrieval, etc. The basic idea of the autoencoder is that the autoencoder can learn the salient features of the data, and it also can map high-dimensional data to low-dimensional for visualization or for dimensional reduction. However, there is still no real way to produce any new content, even when we have the trained encoder and the decoder. At first sight, we may think that we could take a point randomly from the latent space and decode it to get a new content. But the autoencoder is just trained to encode and decode with as few loss as possible, no matter how the latent space is organized. Which means that without explicit regularization, some points of the latent space are meaningless. And also, if our autoencoder model has enough degrees of freedom, we could probably have a zero loss, and which will lead to the severe overfitting problem. So in summary, irregular latent space prevent us from using autoencoder for new content generation. That's why we introduced VAE, a variational autoencoder. So a variational autoencoder can be defined as being an autoencoder whose training is regularized to avoid overfitting and ensure that the latent space has good properties that enable generative process. We can regard VAE as an autoencoder-like probabilistic model instead of encoding an input as a single point. We encode it as a distribution over the latent space. Because VAE involves lots of probabilistic knowledge, you may want to do some refresh about your probabilistic knowledge, and we outline some formula related to the VAE in the second part of this recitation. If you found that if you found that you don't remember any of this in this slide, you may want to pause a little bit and then to review a little bit and then come back to the second part of our recitation. We will also do a basic overview of the generative models. So the task of generative models is to generate new samples, follows the same probabilistic distribution of a given training dataset. In recent years, generative models have shown an incredible ability to produce highly realistic pieces of content of various kinds, such as images, text, and sounds. Among these deep generative models, two major families stand out and deserve a special attention. The first one is the GAN, Generative Adversarial Networks, and the second one is the main topic of this recitation, the VAE, the Variational Autoencoders. So for the second part of this recitation, let's introduce Chris to introduce the detail of the VAE.
Hello again. Welcome back to Variational Autoencoders with your host Chris, co-host Ewing, who just told a really funny joke about generative models. Hope you all laughed at it. Ha 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 ha. Moving on. Moving from autoencoders to variational autoencoders involves a little bit of understanding the underlying relationship between the two, as well as fully unpacking the idea of the generative model, which a VAE is. VAE is the acronym for Variational Autoencoders. It's what the kids use these days. They use VAE. I don't think they like to use Variational Autoencoder. Me, I'm more of a Variational Autoencoder kind of guy, just because maybe I'm just a little bit old school. Maybe I'm not really into the acronyms all that much these days. Nevertheless, I'm going to read you a short poem about variational autoencoders that happens to use said acronym. Okay, here we go. In VAEs, the encoder becomes a variational inference network, mapping observed inputs to approximate posterior distributions over latent space. And the decoder becomes a generative network, capable of mapping arbitrary latent coordinates back to distributions over the entire over the original data space. If I was in a classroom right now and there were a few students here, I would be forcing them to clap. But because they're not, I will clap for myself because I thought I did a really good job. But so what does that mean exactly? So when we were looking at the autoencoder, which is right here, or without all the different colors and stuff, it had an encoder, and then that created some kind of compressed latent space representation, and that was decoded into the original input or some other kind of output that you're looking for. And the relationship between variational autoencoders and autoencoders is mostly within the structural details of the actual models, as opposed to any kind of deeper Bayesian understanding from the autoencoder. That stuff comes from the variational aspect of it. And we're going to get into what this variational inference means. Pretty much it's the fact that this isn't really going to be a deterministic process. We're going to be involving some probability distributions in our sampling for the input to the decoder, as well as thinking about the decoder more as a generator than a decoder itself, if that makes any sense. Let's move on. Okay, so taking a step back into generative models a bit, what is our goal exactly with a generative model? Well, when working with generative models, we assume that our data has some kind of underlying distribution, and we are, in short, kind of attempting to calculate that distribution pretty much. Autoencoders do this to some extent, but leave behind a very discrete space of outputs, as opposed to the more continuous space that you get from variational autoencoders, because we are using probability distributions to represent this latent space a bit more. And we'll see what I'm saying with that in a bit. So we're using maximum likelihood is the intuition behind this framework. So if the model, and we're using maximum likelihood because we want to say that if the model is likely to produce training set examples, then it is also likely to produce similar examples to the training set examples, and unlikely to produce examples that are very different from a model. So if we're trying to predict, or if we're using the MNIST data set and trying to create numbers from 1 to 9 or 0 to 9, you're not going to see a picture of a dragon or something, is all that's saying. So we're trying to maximize the probability of seeing our data under this generative process. So generally, we have this law of probability, I think. I don't know what this is called. But we represent this integral usually in VAEs with Gaussian distributions, where this f of z would be from the encoder usually, but what exactly that f of z is kind of unknown to us right now. In the next slide, you might actually see what it is. But this slide is kind of just introducing the idea of what our generative model is trying to do, as well as just setting up the whole probability space. And you can look at the definitions here if you want to. So question 1, how do we define our latent variables now? Similar to the autoencoder, we don't want to explicitly write out our latent, each dimension of our latent space by hand. We want to use some kind of more complex function to learn the relationships in our latent space for us. So what do we do in deep learning? We use a neural network to define the latent space variables. Differently from autoencoders, we aren't just taking the output and then feeding it into the decoder. We're saying that the input to the decoder will be drawn from a sample from a Gaussian distribution, which is how we are attempting to ameliorate the issue of the discrete output from the autoencoder, leading to the poor interpolation between the points. I hope that makes sense. Moving on. Oh, question? No? Okay. So back here we have this integral over the latent space, but we don't actually know how big this space is. So it's kind of intractable at this point. So how could we solve that problem? So VAEs, this is the main thing about VAEs, that they use the sampling procedure to make it faster. They use a faster sampling procedure. The key idea behind variational autoencoders is to, I'm just going to read off the slide, is to attempt to sample values of Z that are likely to have produced X, the data, and compute P of X just from those samples. So this means that we need to create a new function, Q of Z given X, which can take X and give us a distribution over Z values that are likely to have produced X. So given this Q Z of X, this function that we just made up, which could be anything and might not even rely on X, we can now easily produce P of X given Z relatively easily. So we know how to define the latent space. We kind of know how to deal with this integral now over the latent space. So we need to be relating this conditional probability, P of X given Z, to P of X now. And we can do that by minimizing the KL divergence between Q of Z right now, which is this unknown function, and P of Z given X. So this is the KL divergence, which hopefully you've seen before. This can, by definition, equal this expectation. Applying Bayes' rule on the P of Z given X will spit out these log probabilities, and you can pull the P of X out just by, because it's not dependent upon Z. Rearranging this equation can spit out this equation, and then you can just kind of think of Q of Z. Before we weren't really taking into account before Q of Z was just some random function that didn't have to depend upon X, but we can just kind of throw it in there that it does depend upon X, and reconstruct it to look like this, so it looks a little bit more like, I didn't include it yet. I know this one. No, this one. Just a little bit more like this. Yeah. We were here. Okay, so looking at this equation now, this equation after it's reconstructed. After it's reconstructed, the left side of the equation, or this side of the equation, the right side, it's now a lower bound on this log P of X, which is the thing we're trying to maximize. That's because KL divergence technically has to be positive or non-negative. So moving this back over here would just make this number larger, which means that this here is a lower bound on log P of X itself. And this equation is also known as the elbow, which you may or may not know about, depending upon your background with probability. But let's look at this reconstruction now a bit more. So the the left-hand side of this quantity has the left-hand side has the quantity we want to maximize, log p of x, plus this error term here, which makes q produce z's that can reproduce a given x. And the goal with this is to make this KL divergence go to 0 because we're trying to maximize this equation. And the right-hand side here is something that we can actually optimize via SGD, stochastic gradient descent, given that Q is actually differentiable. Oops. So talking a little bit more about this, we are actually maximizing log p of x here while simultaneously minimizing the KL divergence here. And the reason why we want to look at this equation more is because p of z given x isn't actually something that we can compute. It's intractable. However, this is not, because it doesn't depend upon p of z given x. So what we can actually do is take the gradient of this side of the equation and get something that looks like this, which we can now optimize using SGD in different ways. One more thing is that this really only works when q of z given x is an adequately complex enough function to recreate this original p of z given x, because if it isn't, then this term won't be going to 0, and ideally you'd want this term to be going to 0. So q of z given x needs to be a complex enough function, which saying that hopefully gives you some intuition about what it's supposed to be, which we'll talk about in a second. Kind of going over this loss a bit more. So when we were trying to minimize the KL divergence, because we wanted to understand the relationship between, because we wanted to maximize p of x to begin with, and we used this sequence of equations to figure out that maximizing p of x is the same as minimizing this equation, this being a lower bound on log p of x, because this is, if this is pulled over here, this would be positive. So we're going to be trying to minimize this equation now, which is a lower bound on log p of x. So minimizing KL divergence, maximizing elbow. So we have this loss function, and this is the negative reconstruction loss. And we'll get to that in a second. But this is the KL divergence between q of z given x and p of z, which actually is a closed form solution, which looks like this and can be simplified, but I mean, you don't really have to understand. You just have to be able to implement it, and you can find code on like PyTorch docs or other implementations of VAEs that implement it already, and it's kind of straightforward after you see it once. But with this negative reconstruction loss, with what I've told you so far, you wouldn't actually be able to calculate this and then backprop through any kind of neural network, because so far we talked about sampling. So we talked about getting the z via a sampling procedure. So this is saying that after this encoder, we're going to take the outputs of this encoder and then feed it into a Gaussian distribution, and then take that sample as the not this one because this is p of x given z, but say this was a q here, we would have the input to our Gaussian would be the outputs of this encoder, and then that sample is used in the decoder. But if we do that, then you run into an issue where you can't backprop through a sample because it's stochastic. It's a stochastic unit in this neural network, and you can't really do that. So you need some way of getting around this problem of a stochastic process happening in a neural network. So that's where the reparameterization trick comes into play. And this will probably, hopefully, give you a clearer understanding of the VAE structure. So far I've been talking about everything on the left here, which is you have some input that gets passed into your encoder. And the encoder will literally create like n many means and n many variances that would then be used as input to this Gaussian distribution, which is then passed into the decoder. It's passed through a function, and then you use this as like, this is the reconstruction loss from here. Whoops. And then this is the KL divergence loss from the last slide as well. But you see that there's a big red box here because you can't backprop through a sample. Oops. You can't backprop through this sample because it's a stochastic process. So to get around this, what you can actually do is sample from something that's mean 0, and the covariance matrix is the identity matrix. And then multiply your outputs from, multiply your variances from the encoder by this sample, and then just add the means to this. And what that's going to do is that's going to give you a differentiable sample now, so that you can calculate this loss and then backprop through the network in a way that's actually possible. So this is just an example, I guess, of variational autoencoders and what they do. So this is a representation of said latent space, after it's been trained on X many epochs or X many rounds, where you can kind of start to see spaces in the variational space that blend well together, and then other spaces that don't, which are kind of probably represented by these big gaps in the data space. And even though, so variational autoencoders, like their whole thing is that it's supposed to be able to bridge this gap between data points. You're supposed to be able to have a clear distinction between, say, a 7 and a 1. And this does happen up here, but it happens less and less down here where your data is more sparse. So to kind of recap this a bit, because it's easy to get lost in all this. You have an encoder that is creating, actually it's easier to look at this one. You have an encoder that is taking in a data point X, and then outputting like n means and n variances. Let's look at this example actually. You then sample from the Gaussian distribution usually, and then you multiply your variances by that sample, and you just add your mean on top of that. These variances and means are also used in the KL divergence, where you're trying to KL divergence is it's a check on how similar I think two probability distributions are. So it's trying to get the thing within the probability distributions to be as similar as possible. And this one's already set as a normal with a mean of 0 and the identity matrix. So it's doing that, So this is the first loss, and then this gets sent to the decoder, which is then used in this reconstruction loss, which, like, say if you're using images like here, so say you're like using the number 6, you could use mean squared error, or like binary cross entropy loss, or regular error, or like L1 loss or something. This can be dependent upon the problem itself. Yeah. So, is there anything else that we need to go over? I don't think so. Yeah. So this is supposed to be just a general introduction to variational autoencoders. And there are quite a few references that we have here that we use in helping create this recitation that we think would be a good source for you if you wanted to learn more about variational autoencoders, as well as like the PyTorch example, which kind of gives a good, clear explanation of this in code. And then sometimes reading things in code is usually how I learn a lot of things. But we don't have any code for this recitation, mainly because there's no homework assignment where you have to use a VAE, though there will be quizzes about variational autoencoders. So I hope that this recitation was good and that you learned something, and that we provided enough resources so you can continue to learn on your own. Yep. I hope that everybody's having a good time out there, and that you're going to do well in the VAE quiz, which will be, I don't know actually when that quiz is going to come out. But when it does, you'll be ready, right? Yeah, you'll be ready. Okay. Good luck out there. Have fun. See ya.